Here we go. Math and science, everybody's favorite. Keisha ran out of time and could not complete the lab on motion. However, she turned in the results she recorded before the class period ended. She included the graph below as part of her report. Keisha correctly predicted how long it would take for an object to move 3 feet. If she calculated the speed to be 0.33 feet per second, what was Keisha's prediction? Let's box our question and then look at our table. It's always very important that when you see a table or a chart that you inspect it thoroughly, that you know what it's talking about. So if I look at this chart, I see that it's comparing time and distance, which we've reviewed this year. And I can see that the distance is changing over time. I can see that this is not a very fast object at all because it's not steep, and I know steepness relates to speed. And let's look at what we want to answer here. She calculated the speed to be 0.33 feet per second. So what was her prediction? It says she predicted how long it would take for an object to move 3 feet. So time when distance equals 3 feet. Well, if I go on my graph and I go to distance 3 feet and I move all the way over, I can see that that's not on this chart, which is not super helpful. But we can kind of guess where this line would land because I can guess that it's going to keep moving in this straight, constant line, which would land about here. Okay? Let me try that one more time. This constant line. Kind of lands where 9 would be. But if we can't visualize that, we can always use some math, which is awesome. What we need to know is that speed is all about how much distance you go in time, okay? Like if I go 60 miles per hour, that's because I go 60 miles in 1 hour. So speed always equals distance divided by time, miles divided by hour. Here, my speed is feet divided by seconds. I'm gonna rewrite this down here. Speed is equal to 0.33 feet per second. So that is 0.33 feet that we will travel in 1 second. Okay? I don't want to know how long it takes me to go 0.33 feet though. I want to know the time that it will take me to go 3 feet. So what we can do is set up a proportion, which we are hopefully familiar with from math. Okay? Feet on top, seconds on the bottom, but I don't know what this is. That's my variable. Okay? So if I don't know what this is, let's go ahead and solve. I'm going to ask myself, what number do I need to multiply 0.33 by to get 3? Okay? What number do I multiply 0.33 by to get 3? That's going to be the same number that I have to multiply down here. Okay? So if I were to ask you, what number do I multiply 2 by to get 10? You would say 5. Well, how do I figure this number out? You go ahead and divide backwards, okay? Because whatever I multiply by to get over here times 5, I also divide by to get back. 10 divided by 5 equals 2. And 10 divided by 2 equals 5. So let's do 3 divided by 0.33 is going to equal 9.1. So if I multiply by 9.1 on top, I'm going to multiply by 9.1 on the bottom. 1 second times 9.1 tells me that we go 3 feet in 9.1 seconds. What answer is the closest to that? B. Number 2, the diagram shows several positions along the path of a roller coaster. Which of the following correctly shows the relative amounts of kinetic energy of the roller coaster car at positions A, B, D, and F in order of decreasing amounts of kinetic energy? Let's go ahead and box our question. These can get tricky when we have to put them in the correct order, because I don't want you to understand the whole question but then choose the one that goes in the opposite order because you're not understanding what it's asking, okay? So this is talking about kinetic energy, which I know is motion energy. And we've studied roller coasters a lot this year. We know that on a roller coaster, you have the most potential energy when you're at the top of a hill. You have a lot of kinetic energy when you are at the bottom of a hill, because all of that potential to fall actually turned into motion. And you have the most motion when you're at the bottom of the hill. That's when you're traveling the fastest. So I've got potential, kinetic, potential, lots of kinetic at D, potential, and kinetic. Okay? The amount of kinetic energy at each of these stops is relative to the amount of potential energy it had before it fell. So at A, we have the most potential energy, which means that that is going to turn into the most kinetic energy when it falls. At C, we have less potential energy, meaning we're going to have less kinetic energy here at D. And then at E, we have the least potential energy, meaning we're going to have the least kinetic energy at F, okay? But still, where is a lot of our kinetic energy? At B, at D, and then at F. So let's say we're going to put this in order of decreasing amounts of kinetic energy. That's going to go from the most kinetic energy to the least kinetic energy. Well, I know B, D, and F is where I have the most. Where is the most between those three? It is at B. This is decreasing because I'm starting with the most and going to the least. Then D. Then F. Then I have my potential energies, okay? Wherever I have the most potential energy is going to be where there is the least kinetic energy, okay? But we actually, if we know this part, we can answer this question, okay? Because A says that A has the most kinetic energy. A does not have the most kinetic energy. It actually has the most potential energy, so it has the least kinetic energy. Same thing with B. C says B. Okay. D. Good. A and then F. Looking at this picture, does A have more kinetic energy than F? No. Okay. A is where there is the most potential energy, meaning that D is my correct answer. Okay. Number 3. An athlete can run 9 kilometers in 1 hour. If the athlete runs at an average speed for 30 minutes, how far will the athlete travel? I'm going to box my question. Underline important information. So it says that my speed is 9 kilometers in 1 hour. 9 kilometers in 1 hour. If the athlete runs at the same average speed for 30 minutes, that's my key here. I want to know if I run for 30 minutes, how far will I go? So I want to know, what is the distance when time equals 30 minutes? Let's set up a proportion. First, I've got minutes, and then I've got an hour. So I'm going to turn my hour into 60 minutes when I rewrite this, okay? So 9 kilometers in 1 hour, I can change that to 9 kilometers in 60 minutes. Is going to be equal to how much distance in 30 minutes? Well, I can look at the bottom and say that I divide by 2 to get from 60 minutes to 30 minutes, I divide by 2. So I'll do the same thing on top. If I divide by 2 on the bottom, I got to divide by 2 on top. 9 kilometers divided by 2 is going to equal 4.5 kilometers in 30 minutes. C is the correct answer. If you are able to do this in your head, you can also just think 9 kilometers in 1 hour. How far did I go in 30 minutes? I would have had to go half of that because I know 30 minutes is half of an hour. But this is how we work it out mathematically. Number 4, which of the following is an example of the conversion of kinetic energy into potential energy? So it's going to be really important that we remember that kinetic is moving, motion energy, and potential is our ready to move energy. It's stored. It's not moving right now, but it's ready to move either because it's got height or it's got chemicals that want to burn up, or it's got elasticity, like a stretched rubber band. A says a bicyclist cycling down a long hill. So, if I got a bike going down a hill, I want to know that my kinetic energy is turning into potential, which means my motion energy has to be decreasing and my potential energy has to be increasing. Well, if I'm driving my bike down the hill, my motion energy is going to be going up because my bike is going to be getting faster, and my potential energy is actually going to be going down because my height is going down. That's the opposite of what I want, okay? I want my kinetic energy to be going down and my potential energy to be going up because I want kinetic turning into potential. So A is wrong. B says a car moving forward down a long driveway. So if I think about a car going down a driveway, its kinetic energy is going up because its motion is going to be increasing. Its potential energy is going to be going down because it's moving down in height. So B, again, is the opposite of what we want. C says a basketball heading towards a catcher's glove. So if a ball is being thrown to a glove, the kinetic energy may be decreasing, but the potential energy, there is no change in it, okay? There's no change in height, there's no change in chemical, there's no change in elasticity. So C is incorrect. And then the last one, D, a roller coaster car moving toward the top of a rise in the tracks. So a car going up a hill. Now its motion energy, its kinetic energy is going to be decreasing because we know we get slower as we get to the top of the car. But as we get slower, we also gain height, okay? So my potential energy is going up. And that is what I want. I want kinetic energy, which I have as I go up, turning into potential energy, which I have as I go to the top. So D is our correct answer. Number 5, Maria plotted a graph of her data and she wanted to include as part of her report on motion. What conclusion did Maria correctly make? So we see another distance over time graph. A says the object slowly increased its speed. Let's box our question. Is that a conclusion we can make? Well, I know that speed equals steep, okay? However steep a line is its speed. So this is telling me that we're slowly increasing in speed. If you are increasing in speed, you are also increasing in steepness. What does that look like? To increase in steepness, it means my line is getting steeper and steeper, like this. I don't see a curved line here. I see constant speed, okay? There is constant speed because there is constant steepness. It is the same steepness all the way down the line. So A is wrong because the line is moving at a constant speed. B says the object did not display any motion. That's not true. I see the distance being traveled, okay? I see that in this first hour, we traveled about 30 meters, okay? So did not display any motion, that's not true. If it didn't display any motion, then it would be a flat horizontal line. And the line is not flat horizontal, meaning it is not standing still. C, the object maintained a constant speed. That is a good looking answer because we said that before. If it's a straight line, it's moving at a constant speed. Straight line equals constant speed. And D says that the object changed direction as it moved. I see here that our distance, we're getting further away from something this entire trip, okay? I'm maybe 18 away at this point, and then 30 away at this point, and then 40 away at this point. If I was changing direction, I would see this line kind of do a zigzag. Like maybe I'm going 18 away, and then 30 away, and then 40 away, and then, oh, I forgot something, so I have to go back home. And my distance would be going down because I'm getting closer to my relative point. So D is not true. Why? Because the line moves in the same direction the whole time. The line does not change direction. Number 6, the diagram below shows the path at which a ball bouncing on the ground. 4 locations in the pack are identified with numbers. At which location does the ball have the greatest amount of kinetic energy? So I want to know, where does it have the greatest amount, the most kinetic energy? Kinetic means motion, energy. I know that I have a lot of potential when I am high in the air, and I have kinetic as I fall down, okay? Because that's potential energy turning into kinetic as I drop something. So where does it have the most kinetic energy? It's going to have the most kinetic energy when it is dropped from the highest point. Why? Because right here, I have the most potential energy. That is going to turn into the most kinetic energy. This is the same thing we saw in this roller coaster question up here. The most potential energy turns into the most kinetic energy. So that tells me that location 1 has the greatest amount of kinetic energy. And number 7, look closely at the graph below, which plots the data that were recorded for a moving object. When was the speed of this moving object at a stop? So a stop on a distance versus time graph. Stop on a distance versus time graph is a flat horizontal line. Why? Because there's no distance moved. I'm not going up on my y-axis. There's just time passing. Okay? So if I look here, distance is going up. Distance is going up. Distance is going up. Distance is going up. At this moment, distance is not going up. It's staying the same over time. And then distance is going up. Distance is going up. So it's where this red line is at. Where is that red line at? Between 4 and 5 hours. So C is our correct answer for number 7.